যাই না এটা নিচে এটা নিচে ফেলে দিয়েছি চাবিটা রাখো
হ্যাঁ জিপিএস কন্ট্রোল করি তো স্টার্ট
So good morning everybody. The luminaries on the dais, our respected Professor Tarun Kantijana, the Dean of School of Engineering.
ऑन करो पीछे
I welcome you all on the very third day of AICT Training and Learning Academy sponsored FDP on application developments in the lab on a cheap technology for fluid and thermal sciences. So today as speakers we have got Dr. Rajaram Lakkaraju, who is presently working as assistant professor in the Department of Mechanical Engineering of IIT Kharagpur. We are having with us Dr. Chirodeep Buckley, who is assistant professor in the School of Energy Science and Engineering of IIT Kharagpur. We are having with us our respected head of the Department of Mechanical Engineering and coordinator of this Atal program, Dr. Gautam Ghosh. We are having with us Professor Devdatta Ghosh, who is the associate professor of Department of Applied Electronics and Instrumentation Engineering, as well as the in-charge IIPC. And we are having the participants, mostly the faculty members from various colleges, and the volunteers and the student members. So at the outset, we would like to, it's very customary according to Indian tradition to receive our dignitaries with, Uttariyo. Uttariyo shows a spectrum of honor of gratitude which can be extended from the institute side to the Indian side. Ms. Khai Sharma is doing the honor on behalf of the department. Now I'd like to request to hand over the plate to the distinguished speakers, and I'll request to do the honor to Dr. Ghosh. Now I'd like to request Dr. Tarun Kantijana, the Dean of School of Engineering, to hand over the memento and diary on behalf of the institute to the distinguished speakers. I'm requesting Dr. Devdatta Ghosh to extend the plaques to the honorable speakers. So now we'll be entering directly to the technical session, and with the hope that you will be highly benefited with the speech which will be delivered by the speakers today. And they have taken a lot of pain to come to, they are having, in spite of their busy schedule, they have come to India to enlighten us with their magnificent knowledge, subject knowledge, and which is certainly with this expectation I'm keeping on behalf of the participants that you will be certainly fulfilling the needs and queries of us pertaining to the subject of the concern. Thank you, sir. Thank you once again on behalf of the college as well as the department. Dr. Rajaram Lakkaraju is presently working as assistant professor in the Department of Mechanical Engineering, IIT Kharagpur. He did his BTech in Mechanical Engineering in the year 2004, MS Engineering from Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore, in the year 2007, and Doctor of Philosophy from University of Twente, Enschede, and Netherlands, in the year 2013. He has bagged a number of awards and honors, which includes, BRN's DA's sponsored award, Young Scientist Research Award, Young Scientist Scheme Award, Inspire Fellowship, a Form Fellowship, DST Fellowship, and he scored a very good, percentile in GATE in the year 2004. And he has already, completed 9 to 10 sponsored projects and consultancies. He has been referee for different journals of reports, near about 10 to 15 journals of international stature. He has reviewed papers, and as a teacher he has developed vast curriculum, just like computational fluid dynamics, two-phase flow, fluid mechanics, and many more. And he is having a very good industry academia collaboration with Tata Steel, Tata Steel raw metal processing division, etc. So this is the brief, bio sketch of Dr. Rajaram Lakkaraju, and we are having Dr. Chirodip Bakli, who is assistant professor in the School of Energy Science and Engineering, IIT Kharagpur. His research domain includes thermofluidics, renewable energy, interfacial phenomena, and molecular dynamics. He obtained his BTech and PhD both from IIT Kharagpur. His research focuses on unveiling molecular phenomena under confinement towards modulating fluid and heat transport. Thank you, sir. Now the stage at podium is yours. The session is yours.
Professor Atal. इनको पता है?
ऑटो
ठीक
स्टिमुलेट लिंक तक
हाँ
स्टिमुलेट लिंक तक देना
দিয়ে দিয়েছিল ওটাই অফিসে ফোন করতে
ওটা লিংকটা আপলোড করতে হবে
হ্যাঁ লিংকটা দিয়েছো হ্যাঁ লিংক দিয়ে দিয়েছো অফিসে দিয়ে দিয়েছো আমার দিয়েছো
এই সাইডের দুটো দু সাইডের দুটো মাঝেরটা বন্ধ করে ওবালা অন করে
Good morning, everyone. This is Raja from IIT Kharagpur, and first of all, my sincere thanks to Haldia Institute of Technology for inviting me to share whatever the knowledge I have and perhaps with you. And it's a wonderful campus. It's a very big institute, and special thanks to our professor also for inviting. And I just want to gauge the audience, like, are you from this college or from different colleges coming and participating?
Mostly from this college, mostly from this institute.
I see. How many of you are from fluid mechanics, thermal kind of sciences?
Yes, I believe your hand.
Okay. So what I will do is, basically the kind of works what we do, something named computational research. What are the basic components required for that, how we do that kind of knowledge, I will try to share. So the talk is basically I work on computers, but these computers are bit large scale, like supercomputers what we call. Our IIT Kharagpur has that kind of supercomputing facility. So it will be having something like thousands of computers assembled on chips, so that one will be in a position to simulate large scale fluid mechanics, thermal kind of problems. For example, here there is a racing car. One would like to really design the racing car according to aerodynamics, the exterior part of the floor, which mainly offers drag on that. So there always be some finite amount of fuel inside the car, what you will put. One, you want to achieve high speeds, how strong your engine is designed. Based on that, one will be in a position to achieve that big thrust. The other thing is how carefully you might have this engine component with the thrust. End of the day, it has to overcome air. Unless it overcomes that, which basically all the fuel you are using in the car is to burn, so that you will get the thrust. Finally, race against the wind. So all that energy drains out in the form of drag, and you reach certain distances, maybe speeds. So the main component comes how air relative to this vehicle really flows, and that usually people earlier days go with experimentation, maybe change tire size supposed to be of this size, maybe body size supposed to be of this, is supposed to have different kind of structural integrity people used to look at. But later on people realize that fluid mechanics contribute a lot, especially aerodynamics. Is there a way one can fine tune that? One way is experiments, but every time changing the experiments and constructing that is bit difficult task and money consuming. Computers helpful in terms of tweaking the geometries, try to understand how this aerodynamics happens, finally calculate pressure distribution over that, maybe viscous forces acting on that, how much drag it really consumes. And sometimes this air motions also destabilize these racing cars. For that purpose, how one can really use computers and what are the basic ingredients even to do that kind of research, what I usually work on. And that entire thing, what we call high performance computing, especially for mechanical engineering things. Instead of having desktop kind of computers, you will use large scale kind of things. One of the aspects is air motion over these engines. Other aspects are how combustion takes place inside the engines, how different phases like liquid droplets converting into evaporation, participate in combustion and so on. All these things, in some sense, we write equations, use computers, try to solve them. And our group name basically we call turbulent interfaces and dispersion. Basically, wherever fluid mechanics turbulence happens, that is the place where we try to understand what's going on. And some of the important applications like sprays, something about marine propellers like cavitation and propulsion, and something about chip cooling kind of technologies where two phases are involved, something about oil, gas, refineries, fluid flow, fluid extraction, something about day-to-day refrigeration, air conditioning, where you will have some fluid because of heat and mass transfer kind of effects, phases changes, how to understand it. Though variety of applications are there, the basic ingredient is something like mass conservation, momentum conservation, energy conservation. How to solve that for variety of boundary conditions, we will try to understand. When I am speaking, maybe my lungs are pumping air inside, pushing it outside, maybe my vocal folds are oscillating so that acoustic tune, finally that entire acoustic comes out. These things one can even simulate at computers by writing down equations, applying suitable boundary conditions, try to get the results. So all the computational research is all about writing certain equations, solving them with boundary conditions, maybe certain initial conditions. Especially high computation means you use very massive computers. Even nature-inspired problems like the floods or perhaps dam output kind of things, maybe volcanic eruptions, all these kind of nature-inspired problems, maybe aero-related kind of problems like gas turbine engines, when helicopter is trying to land, the kind of dust which really enter these propeller blades and enter the engine, maybe the missiles exhaust, all these things in some sense connected with different kind of phases. One possibly solid material, the other one is your exhaust gases. Maybe in other cases droplets will be there, fine mist kind of thing, which are participating and going into gases. So you always see phases. That kind of works what we call multi-phase flow research, and basically we try to do that. Try to convert into smaller kind of problems like sprays, boiling, perhaps something about wave breaking. This is the way we break down the entire big engineering problems into tiny toy models, try to understand. So now coming back to today's thing, what exactly about this computational research, what it means CFD, a little bit information I will try to share. How many of you already had idea about CFD or use computers, try to solve the things? Okay, fine. So we will go very briefly what it means CFD. So basically overview how the CFD is popularized after Second World War, what are the complexity, nitty-gritty things involved with CFD, where exactly the CFD is useful, and what are the future directions in which CFD is moving. Computational fluid dynamics, what we call CFD. So the very first thing, overview. Possibly there is a racing car and one would like to design it in a better way. For that purpose, one can do experimentation by designing, investing a lot of money. The other way, try to develop some domain around the object. For example, I am the person who is walking in this room. Relatively, air is also moving over me. So, over this entire domain, I will try to solve equation at this point, at this point, at this point on my body and surround mine. Same thing for automobiles. Around the object, not inside the object, around the object, whatever air is there, we write certain equations, solve them. And that we try to seek a solution at discrete points. The process, wherever I am showing, instead of every location, we carefully choose in this room divided into blocks. So this block, this block, this block, above that, we will try to solve some conservation of mass, momentum, energy, and try to connect each of these blocks in a careful way. If I would like to have more accurate solutions, what I need to do is, instead of having big blocks, I need to make it chunks of smaller and smaller pieces. Each of the place, I need to apply these conservation principles and solve them. Where we use many applications like earlier I said, aircraft, automobiles, even biofluid dynamics kind of areas, maybe chemical engineering like separators, cyclone separators and other places. And CFDs have enormous influence at oil and marine kind of industries. So how we solve? In a very abstract sense, we are going to talk, there is always some real world problem. You convert that real world problem into mathematical kind of framework, writing certain kind of differential equations which vary with the time and space. That means when I am walking, I am the one who is trying to push. So my body trying to push air around me. So there is some kind of boundary condition like this object moves with this velocity, my hand might be moving with another velocity. So that kind of boundary condition, we try to apply it on some governing equations of the system. For example, if I am throwing a ball, basically we write F is equal to ma and try to get ma in terms of md square x by dt square is equal to mg. Solve the differential equation to get solution how ball really takes a flight from one location to another location. So there, with the time, with the space, you write F is equal to ma balance, solve the thing without doing experiment. When it is realistic kind of this kind of problems, instead of F is equal to ma, you have a bit more complex nature of the equations. And those equations, though it looks like some partial derivatives and so on, basically if I push, the same mass has to be pushed to another location. If I give certain momentum, it's supposed to get accelerated. If I supply certain enthalpy, that enthalpy has to distribute. So these three governing equations are principles we write mathematically at each and every point. That's what we call mathematical model, and every problem has its own kind of initial conditions and boundary conditions. Maybe if you are taking a pendulum, just make it to swing, you pull it. So that is the initial condition, like at so and so kind of time it has certain kind of displacement. If you are going to give a kick, it has a velocity. So you write such kind of F is equal to ma kind of thing with some initial condition, boundary condition, solve it. In CFD also we have such kind of initial boundary conditions. After that, what we do is we break down the entire partial differential equations into algebraic kind of equations. So there is a procedure, shortly we will see what it means, discretization. Once those equations are there, you carefully write this place to that place, it has to communicate. That means this point minus this point, information is traveling. And develop that kind of algebraic equations. Finally, when we write that kind of thing, we end up with some linear system of equations. X is equal to b. For example, x plus y plus z is equal to 5, x minus y plus 2z is equal to 3, x plus 2y minus 3z is equal to 4. That kind of equation develops or we develop around the object. Far away. Possibly I am the person who is walking, who is talking, whatever these kind of things I want to do. This entire room, we will make it like blocks, how much momentum really comes and how that momentum really distribute onto each of the grid, which follows certain conservation principles. And when we write that, it finally turns out to be x is equal to b. It's more like a bookkeeping kind of thing. It's straightforward. But what happens is, it's a lengthy procedure, like very big system of equations will be there. Any software, whatever we pick, whether it is ANSYS, commercially available, COMSOL, OpenFOAM, whatever the softwares we pick, basic structure is at the back end, that kind of equations are available. You plug by dialog box or GUI, graphical user interface, you plug certain kind of initial conditions, boundary conditions, you import certain kind of geometry, then the back end what happens is discretize this entire object into finite number of points, takes these conditions, then do certain kind of operations, finally gives you output. And that output again converted into another kind of output, and finally we will get a visual. That entire background, what it means solving this Ax is equal to b. So, did you guys ever use any kind of softwares, whether it is structural mechanics or fluid mechanics, thermal, or any kind of software?
ANSYS, fluent.
ANSYS. So, any idea, like, would you like to share your experience, like what exactly you do?
Actually,
It's okay, you can say it. It's friendly discussion.
actually, I am doing the PhD in Jadavpur. So whatever I am doing, turbulence, based on turbulence. So the methodology, whatever we are using, the FVM, volume method. It is a commercial package. We know all this available inside the Fluent, and sometimes we use the several means turbulence model, the KF server model, K omega model, SST model, like that. And based
So
on
you
that, we are
pick
solving and giving some, getting some data, and based on that, we are plotting the other software like that.
Okay. So basically,
In this way,
using some CAD tool, you construct the geometry.
Yeah.
You import the geometry.
It is inbuilt, CAD, whatever the in geometry.
There
system is
itself, you
available.
create the things and you plug certain kind of conditions. Then finally, you will get colorful.
And now I am just switching this job into Python by coding.
Correct.
Yeah.
So the thing what I am trying to say is, all these commercial software have seat. I mean, you don't need to stand. Okay. So all the time, what happens is, you create something, the software does the job for you. Now today's lesson, what we are trying to learn is, irrespective of what kind of software it might be, what exactly happens at the back end. And that procedure, what we are trying to have idea. Once that solution X is equal to B is solved, again we process this back, and that's what we call post-processing. So any colorful pictures, animation, whatever we see, here we are seeing something named streamlines in fluid mechanics. How these velocity vectors and so on things happens, that we visualize via contours, something like pressure contours, velocity and so on. This entire colorful pictures, finally what we are going to get, we call post-processing. Why anyone does this? Handling experiments always be not a trivial kind of task. Is huge investment, and one may not have even control on fine scale information to obtain. For example, what is happening when I am speaking may not be that obvious for outsider person to sense, but one can develop models having a cut section, try to visualize, see when air breathe in, breathe out are pushed and so on. This is the way structural mechanics works, this is the way acoustic happens, this is the way it amplifies, finally comes. These things, in some sense, on humans doing visualization is not trivial kind of task. That is the reason where you will have these mathematical models and you use softwares, try to simulate and visualize. This is just one kind of thing. Maybe some person is having a problem with kidney stone treatment one has to do. How one will really do it? Yes. Okay, if someone wants to really go for kidney operation, pause. Doing the same thing on patient to patient to patient, trying to sense that knowledge is not trivial task. That is the place where all this CFD really comes in. And also what will happen in future, that kind of foresight also one will be in a position to really sense. For example, you want to really test a engine, maybe jet engine. You don't know when the fatigue happens on this turbine place, when it is going to break, because you want to continuously run that jet engine, maybe on and off kind of operation. Is it going to work for 10,000 cycles, 1 lakh cycles or 10 lakh cycles? That kind of foresight, one will be in a position to really do it at computer itself before really developing a model at lab. You will always have fine tweak tuning kind of things one can do. That's what we call efficiency of these operations. Any small changes you would like to have, for example, a racing car, you would like to have a spoiler on the back to reduce the drag. Maybe you would like to stabilize the system. Trying with experiment many times, getting the knowledge, one can very quickly do it at computer. What are the most important things at this CFD level is writing conservation forms of governing equation for any process. Though I am not getting into what is that equation. Basically, conservation form is mass. If it is getting pushed from this location to other location, it just splits. So whatever you give, the same amount you are supposed to see over the time. It may move from one location to another location, but the same mass you are going to see. You apply momentum, is supposed to accelerate it. You apply energy, is supposed to spread. These are the things what will be conservation forms. And that is the place where we bring discretization. For example, let us look at this expression. I think maybe on monitor it doesn't look. Can everyone see there is something like du by dt, some gradient operator, but divergence of some xi is equal to 0 is there. This is some differential equation. How we break that differential equation instead of solving differential equation, because computers are not meant for differential equations. Humans, we can really do integration, derivation and so on. Computers always work on binary, 1-0 kind of format. So they don't really sense what it means equation. So what we have to do is break that equation into algebraic structures. Once algebraic structures are there, can we really convert into 1-0 kind of thing, which is the easiest way of looking at the things. For the purpose, here just I am posing one example. There is something like du by dt, divergence of xi is equal to 0. For that differential equation, if I want to make it algebraic equation, what I am supposed to do is write a Taylor series expansion for unknown variable u because whole point of a differential equation is there is some evolution term d by dt of u, how that u varies with space and time. Maybe if I am throwing a ball, the unknown variable is displacement over the time and space I want to really understand. So if I am writing a ball which is thrown having a flight, d square x by dt square is equal to z, the gravity, plus minus kind of combination, where x is unknown. Initially I know, but when I apply the force, maybe because of gravity, whatever that, it goes. So x as a function of time can I really get. Here, in typical fluid mechanics, fluid thermal kind of sciences, such kind of x is u, unknown variable, maybe velocity, maybe temperature, maybe density, these kind of variables. How that variable varies with the time, space, every location in the room, I would like to know. For the purpose, what we do is something named using Taylor series expansion. So u, we write it like as a function of two variables x and time. Especially what we do is x at futuristic times, what we want to know. When you are throwing ball, you know the present situation of x, but future time n plus 1 we don't know. T naught initial time we know, t1 time where it will be we don't know, t2 time where it will be, t3 time we don't know, t4 where it really lands up we don't know. So whole point is, can I really track that evaluation, sensing what will be the new position at new time t1 with respect to t0, what will be t2 with respect to t1 and t0, what will be t3 location, x3 location with respect to t2, t1 and t0 kind of thing. Same thing in fluid mechanics, thermal sciences, what will be the velocity information at this space, at that point, at this instant of time and future times. So any information what I am going to seek is in terms of present situation and future with respect to the boundaries, how it really varies. That's what we mean Taylor series. So we write u as a function of x comma t as t n plus 1 as u at x comma n. I'm just looking for a piece of chalk. If it is, it becomes easy for them. So it's okay, don't worry.
Okay, sir. I'm taking.
So what we are trying to look at is as a Taylor series expansion. Any futuristic time n plus 1 information is just a symbol. Can I write it in terms of present plus derivatives in terms of future? F of x plus h is f of x plus h multiplied by f prime x plus h square by 2 factorial f double prime x and so on. Here what we are trying to see is, thank you, u present plus futuristic kind of derivatives what we are trying to do. So whenever I would like to really know del u by del t in the equation, if I really discard these higher terms, something like f of x plus h, if I want to approximate for one dimension x, we will be in a position to write h f prime x plus and so on, so time. These things, if I am ignoring, saying that small, I can always find what might be f prime x in terms of these variables as x plus h minus f of x by whatever that gap h. Instead of equal, we use approximate sign. So if my equation is, in case f prime is equal to f, which is df by dx is equal to f, equation if I want to do, the entire differential term, I am going to replace it in terms of algebraic terms, approximately by h in a approximate way. F calculated right now at x location. So if I am going to rearrange, maybe my f of x plus h next spatial location turns out to be f of x multiplied by 1 plus h. So next spatial location I will approximate. Once this is known, the next one again recursively I will use and go ahead and solve. The same kind of things in computers, especially CFD, what we do, how complex might be the equation, can I really replace the derivative equation in terms of algebraic expression? Because x location I know, x plus h I need to know.
So in your assumptions, derivative of f is equal to f. What is the interpretation?
So this is one kind of mathematical model what we are trying to say, something like exponentially growing kind of thing. There might be population growth happening, some kind of differential equation is available. Here in an abstract way I just wrote it like, if I have some differential equation df by dx is equal to f, I want to get a solution, how I can teach a computer.
Now, in your assumption, the derivative and function both are same. What is the significance? F dash x equal to f.
Correct.
So some change are there, and which is equal to the original function. What is interpretation?
You mean, is there any connection with reality kind of example? Possible. For example, if I am modeling some stock market, let us assume this equation may not be applicable. How much stock I have, based on that I can invest more into the future.
After sometimes it will be changed. If you say some stock deviation, so if you differentiate means with respect to time it will change.
Correct.
And that change is equal to that function.
Correct. Possibly something like if I have more money.
Suppose I have stock price is 2000. After some time, after 10 minutes, it is same.
It will be same at that given instant of time or at that given instant of location.
Okay.
So this equation, what it tells us, df by dx is equal to f of x means you propose what is the x location, that f of x value it will be equal. Maybe x plus h location it will be equal to that function. So algebraically if we are trying to talk about df by f is equal to dx, the solution itself is something like log f is equal to some constant. So your function exponentially growing kind of thing. I have more right now something like 1 lakh rupees. I am ready to invest maybe 1 lakh into stock market to make it 2 lakhs next time. When I have 2 lakh, I might be going to invest that 2 lakh into make it something like 4 lakhs. Maybe I am going to really increase based on how much money at present I have. I am not saying that that is generally applicable for everything. But in case, if I have such kind of equation, how I can really teach a computer to convert differential equation into algebraic equation. So the entire message of this is, even though you have conservation principles, reality and so on, you end up with some kind of differential equations in the system. Your computer may not be in a position to understand it. Now, can I really teach it in a better way, what it can be good at? Instead of asking computer to learn differential equation, it is good at algebraic expressions solving Ax is equal to b. So what we are trying to do is, in very abstract way, can I really convert my language into computer kind of algebraic languages? What computer can do is, I can just put a loop for I is equal to 1 to 10. Repeat this process every time to solve it. It is much easier for it compared to solving them. The same thing happens at CFD. We may have complicated equations, but those complicated equations somehow using basic structure named Taylor series expansion, write it, track it, bookkeep it very nicely, build that kind of code, solve it. And that in a very abstract and pictorial way, if we are showing, this entire mathematical expression is maybe some curve which I want to really predict. At one location I will take, that location I will calculate df by dx kind of information by neighboring points. Here the neighboring points are there. And that, if we are going to scale it up, more complex equations we can really solve. This is the essential step of CFD. Any derivatives, how complex might be the equations? Something like del square u by del x del y, del u by del y, and so on, so kind of thing. One will be in a position to really discretize, write it like neighborhood points. So possibly, again in abstract sense, whether it is x, whether it is time, discretization means seeking at every given location, but not in a continuous way. This block, next kind of thing. What will be function value? What will be function value? What will be function value? When I know function information is here. Can I really get such kind of function variation? And each of these points in some sense connected with this one, connected with this one. And write down your differential equation at each and every point connected, develop this system of equations. So over the time we will sense what it means. So usually we see such kind of complex derivatives when you are solving fluid mechanics, thermodynamics, maybe heat transfer kind of applications. Finally, convert that into single steps like this kind of algebraic relations. Those algebraic equations, what I am trying to say. I minus 1, I plus 1, j minus 1, j plus 1. These are more like loop kind of structure. Each and every point one has to try. I increases, j increases kind of thing for a spatial dimension. If it is 3 dimension, I will have I, j and k. So first point, second point, third point, fourth point. First, second, third, fourth. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2. The entire space will be discretized. This is the word what we say. And write in terms of ij kind of loop structure. Solve this equation for I is equal to 1 to whatever that. That is the way this entire differential equations we will solve. When we are solving, usually we end up with lot of issues. Maybe writing equation is easy. When you are solving Ax is equal to B, there will be issues. You may not be in a position to invert a matrix. You write that complex kind of expressions, but if you can't really invert that, you don't know how to invert that. Sometimes Gaussian elimination may work. Heard anything about Gaussian elimination, LU decomposition, this kind of thing? These are the ways to solve system of equations. When those things one will not be in a position to do, one has to look for better alternative methods. Sometimes solving by one method is very difficult compared to other way. So in that case, one has to employ new kind of techniques. And that is the place something named consistency, stability, convergence. These are the keywords in CFD what we talk. When you are solving equations Ax is equal to B, now, tomorrow, day after tomorrow, perhaps on this computer, on the other computer, on the other computer, it always has certain kind of memory issues, maybe how many floating points, double kind of things, these kind of things always be there. Are you getting the same solution every time when you are doing? In some sense connected with this consistency kind of thing. More rigorous way one has to do, whether you increase the grid, decrease the grid and so on, you should be in a position to really get that same solution. Whether you use 100 points to resolve it, 1000 points to resolve it, 10,000 points to resolve it, there is something like error when you are estimating. It should be consistently happening. That kind of things what we really reserve this word in a very loose way. There is something like stability issues come into picture when you are solving the equations. You solve it, instead of getting a solution, it start blowing up in the thing. You would like to get 5, first iteration 5, next iteration 6, next iteration 10, next iteration 10,000, next iteration something like 1 lakh, this kind of values happens. So something has to be tweaked. If we are going to do that, we do this stability analysis. Whatever I wrote here, Taylor series, when I am going to do that, is it correct approximation? Should I really write x plus h information minus x by that distance, or x plus h minus x plus 2h by that distance. This kind of issues will be there, and that usually we connect with stability point of view. Convergence is more about your scheme resolution kind of issues. We'll see. So for example, if we have some del u by del theta, consistency means, can I really write that del u by del t as ui at n plus 1 minus ui by delta t? If I am doing that, we call consistency. Already partial derivative term replaced into algebraic term. So can I really solve that numerical solution by discretization or algebraic terms? Usually when you are solving equations, if it is analytical, one can always get something like exact solution. For example, here df by dx is equal to f of x. If I solve it analytically, it is f goes like e power function log f is equal to constant kind of thing, so it will be exponentially growing kind of thing, e power x kind of solution. Here I will be in a position to do that. That's what we call exact solution, but in all the cases we may not be in a position to get it. That exact solution, whatever the numerically we are solving, when the gap between these points are tiniest, that means more and more points we are doing, are they matching? If they match, we call convergence happen. If that doesn't happen, convergence really must. Can I really make a differential equation into discretize via certain kind of rules? Here Taylor series, how many approximation I can do? That's what we call consistency. And I may be having some exact solution, I may be having numerical solution. As I am decreasing this gap in between that, am I really getting the same solution? If we do that, we call that as convergence. It's more like when I am speaking, I want to understand how acoustics propagating. Maybe your solutions happens after every 1 meter, and that is the way you want to solve the problem on computer. Because 1 meter maybe for our persons looks like a bit far. Maybe 1 millimeter is good enough to write equations solved in the domain. But when you are going to solve it on 1 millimeter accuracy, 1 millimeter, 1 millimeter, 1 millimeter, 1 millimeter, you need to have so many points. It's huge effort of the computer to solve it. When you are doing it on 1 meter kind of thing, solution may start spreading everywhere. At 1 meter level, you may not be in a position to catch the solution. Maybe think of, when I am speaking, someone would like to understand how these waves are propagating after 1 kilometer distance. Already these are getting dispersed. He may not be even in a position to really sense what I am talking. Maybe light, he may be in a position to really see if his eyesight is very good. Maybe I am just opening my mouth or something, waving the hands and so on. Computers also does in similar way. If your gap between the grid is so large kind of thing, something like problems with convergence happens. The solution really disperses, diffuses and so on. You may not be going to get accurate solution. So these are the checks what people do at CFD on these procedures. So whole point is, can I have a numerical scheme which is consistent via that kind of Taylor series approximations, and also can I really get one particular solution, exact kind of thing. If both the things balance, then we say that this scheme might be stable. Even on long-term predictions, it's not going to blow up. For example, right now, I might be in a position to get a solution. But over the time, it start wandering, wiggling and creating a lot of disturbances in the solution, which is not good for them. That kind of thing, what we usually check it via stability. For example, think of, I am the person who is speaking. But numerically, think of there is abstract concept like on computer I try to teach. When Raja is trying to talk, acoustic waves are coming, they are propagating. Computer does the job. but the schemes prescribed by the person, if these are not good, what happens is, even short span of time, Raja is continuously talking, what you hear will be completely corrupted kind of acoustic noise you will hear. It's not something locally happening, but because numerics always add certain kind of noise that takes out energy out of the system, brings in energy into the system. Because of that, you start sensing, even though I am clearly speaking right now and so on, what you may hear is, if you do computer simulation, try to get the sense out of it, it might be very distorted kind of thing. So when you are solving fluid mechanics, thermal, whatever these things, you have certain very well established equations. You may know Taylor series approximation. You may use something like first order schemes, second order schemes. These are the technical terms. When you are solving that, you expect that I am prescribing this thing, so I am supposed to get something out very accurately. That may not be the case, because that always add lot of noise and also disturbances into the system. So corrupted solutions really happen, and that you may not know at this point in time, because you may be solving for 0 to 5 seconds. Who knows what will happen after 50 seconds? The entire scheme might be destabilized. You just get completely shabby kind of results. That kind of thing, what people usually check via 3 things: consistency, stability, convergence. We are not getting into deeper parts because it's a short lecture, but these are the crucial words for doing any calculation. Even if someone is using as is, open form, console kind of thing, the stability, convergence, consistency, what scheme is good, what scheme is not good, is very important. The next thing comes, how quickly you will be in a position to really get the solutions. That's what we call speed up of the thing. Maybe you might be using just one computer. Possibly if we have this kind of things, it might be having i7 kind of processor, or perhaps octa-core kind of processor and so on. But when you are going for, that means it may be having 8 very loose ways, 8 sub kind of partitions. Each of the sub partition can do the calculations. Maybe if you are taking your mobile phone, it always have that processor. It does certain kind of operation. You can use browsing, you can play videos, you can listen music, many kind of operations are happening. But if you dump more and more operation, immediately it really gets hanged. The same thing happened for computers also. When your processor is not that efficient in terms of taking the input, processing, giving out of the thing. There are always be cache memories inside the system. How much process it happens on that, how much information you can really send, how much information can happen or come out of the system. And that kind of computers interacting with multiple things when your solution is big. You don't solve all those Ax is equal to B on one single computer. That will be distributed into this part, that part, maybe that part is on that computer, on that part, and so on. Thousands of cores connected with each other. How to distribute that? When you are going to distribute that, naturally there will be latency issues now. Means you cannot transfer information, you might be computing, but how can you transfer it spontaneously? It always have cables, so it slows down the thing compared to your computer. So your schemes supposed to take care of even how one can really go with multiple computers. So what are the requirements for this kind of CFD thing? Something named accuracy. That means solution must be right when you are predicting. Even when you are solving df by dx is equal to f of x, e power x, I want to really get, that is the exact solution. But when you discretize that, instead of e power x, let us draw two curves. Maybe I am beginning something like here. This is the exact solution which I would like to get. But when you are doing computer, possibly you get solution f as a function of x. When you are solving, you might get that information. When you are getting, it might be here. When you are solving, it might be here. Now, the kind of curve what you are getting on computer is instead of e power x. That kind of solutions, what we mean, solution must be right, accuracy. When you are solving, there always be dissipation happens based on these terms. Whether I would like to solve it, I want to understand exhaust coming from aeroplane. How far this entire exhaust, the pollution really disperses in the system. Problem every given second or first second, second second, fifth second, 10th second, maybe 100th second, maybe 1000 seconds, maybe after 1 day, after 10 days and so on. So something like a non-uniform way we are trying to solve. That also matters to get the solution. If you are going with non-uniform, still are you in a position to get accurate solution? That's also one of the important things. Some about like high resolution capability. For example, jet engines and other things, they always show turbulent kind of flows. Using the same schemes, will you be still in a position to really capture that kind of information? May not be. Then what kind of schemes one should really use? That kind of thing, what we call high resolution capabilities. So traditionally, it all began with fluid thermal sciences, the CFD, computational fluid dynamics. The name itself says that, though in the 18th century, like Euler, Gauss and so on, so kind of thing, Runge-Kutta and so on, you must have heard about these names. In 19th century, people tried to develop for small scale kind of problems. But over the time, they really picked up computers, electronics coming into picture. Then people started solving these big equations on computers. And finally, that's what we call CFD. That's the first lesson of the introductory to CFD. Any queries, questions, or perhaps you must be already knowing, so I just try to have a recap over that without going a lot of details into that. Any queries?
Good.
So now what we are going to sense is some kind of history, how that CFD terminology came into picture. We'll see. So for example, there is a fighter plane. One would like to really develop that kind of supersonic aircraft. Supersonic aircraft means when something moves, immediately you start sensing noise. You open a tap, water is gushing out. If you are careful enough, you start sensing something like disturbance, waves, noise is coming. You open the tap bit more, a gushing kind of sound is coming. So basically what is happening is, you have something like a tank, water is coming out because of gravity. It possesses certain potential energy, you are converting it to kinetic energy. With that kinetic energy, this entire liquid water is coming out. But this acoustic noise also have energy which is derived from that potential energy while converting it to kinetic energy. It is going to interact with air, sending ripples, and it starts sensing something like zzz kind of noise and so on. It's draining out energy out of the system. Some part of the energy really goes, and this energy will be phenomenal and dominant when things move at acoustic speeds. Right now, I might be walking at slow. You may not really hear that noise. Maybe river is gushing. You may hear huge speeds it is going. That speeds, if they are reaching at acoustic speeds like 330 meters per second in this kind of normal conditions, when I am speaking, it's not air, but the disturbance waves, pressure waves, acoustic waves propagate with 330 meters per second. That means within a second, they have a capability to reach 330 meters. Whether they may reach before that, they will dissipate, that's different issue. But they have the capability to go all the way to 330 meters in a second of time. So fighter crafts and other things, they go at that kind of height, something like they are prepared to go at 1200 km per hour fighter crafts. That kind of things always have Mach numbers greater than 1. Maybe fighter plane may not be moving at 1200 km per hour, but the flow to get that lift possibly at certain locations on the fuselage, cockpit, wings and so on, they might be more than Mach number 1. So the speed at which flow is happening to acoustic speed of this disturbance is what we call Mach number. When these kind of speeds are happening, whatever the fuel you pumped into this fighter craft, what you want to do is you burn it engine, give a thrust so that it will really accelerate. But because it is already at that kind of acoustic speed, if it wants to really go through that air, it has to penetrate into air. It's more like me walking in air is quite easy. But I want to really penetrate into table, separate it out, go forward is not real task. To do that, I need to spend a lot of momentum and also energy out of the system. When fighter crafts are moving, usually they really spread that air. But if they are moving at that kind of high Mach speed, they have to really penetrate most of the energy, whatever you put in as fuel, get out of the system like waves, shock waves, and dissipates out of the thing. And that is the boom what finally reach you. Near the aircraft is unbearable noise. So nearly 60 to 70% of your energy just goes in that kind of format. The rest only goes to propel it forward. So huge amount of loss happens. The same thing happens even in numerics. So all this CFD accelerated when people started looking during World War to create better and better kind of propelling objects, whether it might be aeroplanes, missiles and so on, so kind of stuff. What actually happens around them, because no one can see it directly with visuals. You may have to use experimental kind of things, Schiller kind of visualization, wind tunnels. Let us look at the small part of the wing. Maybe it may have a cut-sectional shape like aerofoil. So that wing, if I slice it, open it up, maybe the shape looks like that. This is what we call airfoil. And flow comes from one direction, goes. It's more like a relative flow. When I am walking, air is at rest, I am moving the one. The other way is I am at rest, air is moving, relative flow. So when you are solving on computers, what we try to do is, you don't really move the object, you make it stationary, let air comes on. Solving that is becomes easy, otherwise entire body has to be shifted. So what we are looking is flow over such kind of aerofoils. Comes from one location, goes other. Some parts of the zones may show very high speeds kind of thing. That immediately gives ripples, shocks, maybe boundary layer instabilities and so on. These are the keywords in fluid mechanics community, what people try to do. It's not just interesting, but these are the main source culprits for removing your entire fuel or energy out of the system. And that is the place people try to really look at why that happens. During that time, to maintain certain kind of conservation laws across these zones. Something we call Rankine-Hugnoid kind of conditions in terms of fluxes and so on. That is the way this entire CFD started propelling or developing. And people try to come up with how to solve these equations, because without solving equations, you don't know what happens. You can't really measure the things moving with fighter craft. And that at laboratory on computer one can simulate. So when you are solving that, are your numerical things correct or wrong? How to test that? And they try to pick up small toy problems like waves, shocks, how they really propagate. When you are solving, instead of getting this kind of shock, possibly they are getting a lot of erratic kind of things. Now can I fine tune this entire numerical scheme, try to get that and so on. That is the place where a person named Professor Bram van Leer developed a lot of numerical schemes. And most of these schemes for high speed aerodynamics, what we call in terms of compressible flows, hyperbolic equations, what we call it PDEs, which you know, mainly how to solve these hyperbolic equations developed by this person. He is one of the contributors. It's more like standing on the giants of shoulders. So his name is quite popular. With that, many numerical schemes, limiters came into picture. Van Leer kind of schemes. Then later on, these are furthermore advanced, something named muzzle scheme, multi-dimensional upstream center schemes for conservation. These are the technical names. What I am trying to introduce you is some typical jargon which you might have seen or may see when you are going to use software. So these kind of schemes, what he has developed. Especially, is it good enough? Is it stable? What kind of accuracy and so on. So he proposed a cartoon kind of picture, Van Leer's view. So the entire history of CFD relies on main giants like Gauss, Euler and so on, so kind of persons. Something about persons like Philip Rowe and John von Neumann and this kind of guys who mainly worked during the World War kind of time, and based on the things whatever they have developed, he would have really climbed up that big pyramid all the way, which we call CFD, using whatever the developments they have done. So Bram van Leer is one of the greatest persons on this hyperbolic equations solutions. What he says is, whatever the things he has done, he has used all the information what people are trying to look at, like, oh, this is happening, that is happening, gather the information, can I build one more brick over that? So basically this emergence of CFD, one can really connect like fields like aerospace kind of thing, mechanical, computational science, computer science and math departments. These kind of mixture of fields in some sense connected with CFD. So just outlining, because it's history, the most important things developed during 1940s to 50s kind of time. After 50s, you already have electronic computers and things really went into development phase. In 1960s, something like people tried to solve this compressible flows, which we call Euler's equations. Then powerful computers came into picture. People try to solve for planes, commercial planes and so on, so things. Try to capture shocks, how they interact with each other. Something like in 1970s, 80s kind of computer. Huge room, the entire room is occupied by it. In fact, you should really visit our IIT Kanpur. We have a beautiful museum, Nehru Museum we call. It's a scientific museum. There you will see old days kind of computers, how they used to have this and so on details. So please do visit us, so you will have a better idea what's going on. So in a nutshell, in 1960s, they tried to solve something like Euler's kind of equations, then go with nonlinear terms in 1970s, something like RANS, again technical jargon, how you solve equation for turbulent kind of systems in 1990s. In 2000, LES kind of way, people try to attempt on computers. In 2010 kind of thing, hybrid methods came into picture, how to club LES with RANS, LES with DNS and so on, so thing. And these are the strategies to solve CFD in a different application world. The bottommost thing is only for waves. The topmost, whatever you are seeing, is all the realistic fluid thermal sciences kind of problems. Solving waves itself is challenging, but waves, fluid mechanics, heat transfer, these are interconnected kind of fields. One cannot skip this to understand other. So in some sense, it goes within that way. So what you are seeing is something mesh kind of elements, what you are seeing. The bottom thing, this one, is the wing shape. Based on the speed conditions, your wing design really changes. What kind of meshes around that for air you need to use, so that you will be understanding what kind of vortices really comes out, how these unstable oscillations happens on the aerofoil and so on. So some places it is very coarse, some places it is very fine cluster, and people use this kind of meshes which people call chimera meshes. You will have dual kind of meshes which you map and try to solve the things. These are the recent advances. Recent means almost like decade back kind of thing. Now, machine learning also came into picture with CFD, either predictability capability or the schemes. Unless you really go with CFD course, you won't understand about stability, but in a very nutshell, when you are solving equations, this may not be good enough. Can I change this discretization every given instant of time to reach better and better accuracy? For that purpose, machine learning really helps. A few years back, this kind of machine learning based kind of discretization techniques also came into picture. People try to use that to accelerate the computing. For example, think of I want to solve flow over aeroplane, try to understand that. Maybe you require huge computers, supercomputers to solve that, which may go churning the solution for week, maybe 1 month, maybe 1 year kind of thing. But once you understand one kind of problem, tomorrow you want to slightly change the wing shape. Try to understand. Do you have that much time to really get the solutions for that? Or from this problem, can I really understand another set of problems? Is it completely different or in some sense close relevance? At that place, machine learning naturally comes into the picture. How much solution you have? Can I really predict future time, future space kind of thing, or future kind of problems? So it's an hour. Let us not worry about that. Requires bit understanding about discretization. With the time also, can I really tune this scheme automated way? And that kind of possibilities presently happening in the CFD community, which itself is big challenge for computational guys. So usually when people use softwares, initially they will specify, I want to use centered difference schemes. I want to use something like quick scheme. I want to use second order convergence. You fix it. Throughout the simulation, it doesn't change. Now, when you are evolving over the time, these schemes or new schemes itself can one uses. How to use that automated way. And that is the place the future trend is going on. The big, grand, old challenging for CFD is two problems. One, trying to understand jet engine, the flow dynamics. The second thing is oceanic wave breaking kind of things, because that has bigger impact on climate change issues. So these two are considered in some sense bit grand challenging problems. Rest of the things, whatever the problems, fall in between this gas turbine to that oceanic kind of thing, the subsets kind of stuff. So multi-scale issues involved in that problem and so on. So I just outlined year-wise, like you can always get that PPT from coordinators, organizers. What are the era in which we are working in? Nowadays, people trying to club finite volumes with finite element methods, because people would like to really understand better approximation taking care of fluid structural kind of issues. When you have that kind of interfaces, how we can really handle the problems. For that purpose, there is something like emerging area, discontinuous Galerkin methods, finite element methods are coming with FEM. I'm sorry. With that, I would like to, okay, let us see a very brief terminology, maybe 5 more minutes. So maybe in 1970s, computers are 1 megaflop kind of thing. When it comes to 2011 kind of thing, is 2.5 gigaflops. I mean, like if you are opening your computers, like maybe your Dell or perhaps in what do you call, Asus and other kind of things, there always be processor kind of ratings. How many floating point operations it can really do. It's internal thing. The external things are your cache, RAM and other things comes. The processor kind of operations, how many it can really do. Usually we talk about flops. Your MacBook Pro in decade back can do something like 2.5 gigaflops, 10 power 9 kind of operations compared to 1970s supercomputers. Is already went by 4 orders of magnitude in 40 years of time. Nowadays, Intel Xeon 2 kind of workstations, which will be within 2 lakhs, one will be in 1970s kind of time, it must be a huge investment. So, as a timeline, with the time, how much speed one is using, in some sense, exponentially, it is increasing. And for example, in 2010 kind of time, it is something like gigaflop kind of thing, what one will be in a position to really get. Over computational speed means electronics hardware kind of issues naturally comes. Over that, higher order methods means how accurately you are going to approximate the thing gives you double the boost. So it's more like a mixture of both the fields. So with that, I just would like to close these 2 lectures kind of thing. So now the question really comes like, shall we go with the next lecture? Would you guys like to take some 5 minutes break? It's good enough. Thank you everyone. Please do visit KGP whenever possible.
So we enjoyed lots, sir. Nice
Thank you so
lecture.
much.
I'm from mathematics, but your lecture is very nice.
Oh, I see. I guess so. I guess so. If you ask the question.
Nice lecture, very informative.
Thank you so much.
I'm back.
Thank you. Thank you. Thank you for coming. Thank you.
Okay, so the title of this FDP is Lab on a Chip for Thermal and Fluid Applications, and when we talk about lab on a chip, what is the first thing that comes to your mind? You people are from mechanical background, no, different backgrounds. Okay, so that's good because lab on a chip is it encompasses various backgrounds. So typically, when literally it means you develop a lab on a very small scale or on a chip-sized platform. So you basically try to scale it down. So what is the importance of scaling down? So as Sir just explained, the importance of scaling up on computation that comes with an inherent scaling down of size. So we understand that the size of an IC chip has reduced drastically, and the number of ICs that you put in a computer, that exponentially increases with time. So starting from 1950s, in about a century, it has increased exponentially, and now the supercomputer which needed a whole building to be housed, now we have it in our pockets, and our mobile phones are much more efficient than that. But so what is the role of mechanical engineers? So people from instrumentation and computer science would say that they have really developed a lot, but what are mechanical engineers doing? So apparently, for lab on a chip technology, nothing much, because the battery technology hasn't developed as rapidly as the IC technology. Similarly, any transport of say energy, momentum, that on a small scale is sort of difficult. So that brings into perspective how scaling down would help. So, one of the primary requirements of scaling down is the reduction of material. Now, one of the problems that we see that for everything, if we need a lot of material, that would require a lot of material resources, a lot of energy resources. So, by scaling down a process, for example, a diagnostic, where if you are to get yourself tested for blood sugar or something, so you would like to give a bottle of blood. Okay, you would like the process to be as painless as possible, and you want to have the entire process done with the minimum volume of blood or minimum, and if possible, not even blood. Okay, minimum intervention. Similarly, several technologies like for example, electrical power. Now we charge our mobile phones using socket electricity with a regular charger, which has an adapter and our mobile battery is 3.7 volts. Right. But we are charging it from a 220 volt AC using an adapter which is being supplied from a transformer which is at 25 kilovolt, and so on and so forth. So, and if you go to Kolaghat nearby, you would see some coal getting burned and a thermal power plant generating energy so that our mobile phone can be charged so that we can watch reels on it and discharge it immediately. So, talking about lab on a chip technology, there is a sort of disparity between how it has developed, and towards it, microfluidics and nanofluidics would play is playing a very important role and would play a very important role in future in integrating this. How can we transfer energy, momentum, or mass at small scale? So, I believe like you already had 2 days of course on this topic, and you are sort of exposed to microfluidics and nanofluidics. So that is going to be the outline of our talk. So we would introduce what is micro nano, and then we would look into a case study where we would see a pressure driven flow, and finally we would talk about an application which is designing a thermal management system for your smart integrated circuit chip or a battery. So that would be the total outline, but without spending time in that outline, let us try to define what is microfluidics. So microfluidics, as the name suggests, is a study of fluid mechanics where your scales are in the order of 10 to the power 6. So ranging from something below, a little below 1 mm to about 1 micron or 10 to the power minus 6 mm. So as the advantage suggests, it saves a lot of cost because your material would come down, and length and time, they proportionally scale. So the timing of the test would come down. So a few years back during your COVID test, most of us had got tested at some point of time, and waiting with bated breath for that SMS that whether you are being quarantined or you are safe. So you can imagine if the analysis time is shorter and very rapid, that helps. So, but there are certain problems. It is very difficult to visualize. Why? Because firstly, the visible light, the range of wavelength of visible light is from about 300 to 700 nanometers. So it is a little shorter, little smaller than 1 micron. So a micrometer system you would be basically seeing as a scratch, and with most of the people would miss a micron scale system, forget about a nanometer system. So managing a system at micro scale is always difficult. So that is one of the primary challenges, but these challenges are overcome by the huge lot of applications that come with it. So as discussed, one of the primary is biomicrofluidics, where you can analyze any biological fluid using your microfluidic circuit. And so diagnosis is an entire history of microfluidics. Apart from that, you can have small amount of reactions on these genes. Then you can harvest energy at micro scale, which is very interesting because you need not always go and use your grid powered electricity to charge your mobile phone, but you can have, for example, probably a futuristic technology. The more reels you watch, the more your mobile phone gets charged, because that friction with your finger would probably charge your phone. So that sort of some technology can be developed by for a microscale circuit, and so on and so forth. So that's the story of microfluidics, and it has certain challenges. Okay, but those challenges, we would discuss the challenges together with nanofluidics. Those challenges are sort of solvable by the techniques you learned in the last lecture. So you can use the CFD, so you can have that huge PD which is really scary and solve it in a computer, because computers are cheap. You get a lot of computational power. So you can solve it and you can obtain it. But there are certain problems in it. And those problems come as we scale down the system. So below micron, we also get something called nano. So nano is basically 10 to the power minus 9. And nanofluidics is the study of fluid mechanics in confinements where at least one of the dimensions are in the range of 10 to the power minus 9 meter to up to 10 to the power minus 7 meters. Please be careful. This is totally different from similar sounding field which is called nanofluids. Nanofluids is the study of particles which are of nanometer dimensions, and they can be anywhere in a micrometer dimension or a nanometer dimension or a millimeter dimension, anywhere. But nanofluids is the study of such fluids. Now, what is the challenge of handling computation in nanofluidics and microfluidics while we are solving it in a computer? So, the challenge is here. So, classical CFD very beautifully would approximate these higher order terms as small, and they can be neglected to write a beautiful equation like this, and you can convert your entire derivatives into differences and solve algebraic equation instead of your partial differential equation. But what if I tell you that this need not be small? So with confinement, what happens? Your gradients change very sharply. Like your say very near to the interface, we all say there is something called a no-slip boundary condition. Fluid next to a solid surface which is stationary would not move, because the fluid molecules would interact with the solid surface and they would exchange their momentum and energy completely. And it is a typical thing that, like all of you are teachers, so you administer huge classes. So typically it would happen, the students sitting on first bench, you can govern them more properly, so they would remain stationary, but at the back bench they are at their own will. So similarly, for a channel carrying fluid, that also happens, where the fluid next to the wall is stationary, but at the center it is moving. But as you scale down the system, you do not get sufficient interaction. Okay, so for a very small system, the fluid next to the wall might also be in motion, or vice versa. So that complexity makes these derivatives extremely complex, and hence the traditional techniques of CFD that we have used for about 50 years for solving these are sometimes they fall short of the of solving these equations. And but nonetheless, because of the huge application, we need to solve it. So we would go into techniques of solving it, but just to give you a little bit of motivation, we would discuss what is the difference between a continuum scale and a molecular scale. So traditionally CFD is same. It is solution of some fluid mechanics equation at either microscale or nanoscale. But the difference is that as we approach from below micrometer scale to a nanometer scale, we are approaching a particular scale. And what is the scale? This is the scale of molecules or particles which the matter is composed of. For example, a water molecule has a diameter of about 3 nanometers. 0.3 nanometers. Similarly, larger molecules would have larger diameters. So you are sort of in a situation where you can typically count the number of molecules that would be filling the channel. And in that case, using an equation like this as a Taylor series expansion is not always sufficient. But But why do we need to look into those things? Because at the end of the day, if sir put up some very beautiful examples of jet engines flying, fluid flow through pipe, but in all those examples there is always a fluid solid interaction. Okay, the entire money of the aircraft, the fuel expense, goes into the fact that there is a skin of the aircraft which is rubbing against the air, and that is causing friction. So your fuselage is burning because of that. Similarly, for most of the example, there is a sort of a fluid solid interaction which is basically the thing that you are paying for. Similarly, your water tank. Okay, so you need an overhead tank, a pump to pump into it, because there will be some friction to bring down the water. Otherwise, if a tank is there, it would automatically carry the water. So that interface is very important, because there is a lot of things that would go into the interface, and that fluid solid interaction at the interface needs to be understood. And this can only be understood if we look into the dynamics of that thin film, a microscale or a nanoscale film next to the surface. And there are several examples. For example, you can design self-cleaning surfaces. So surfaces which get cleaned automatically. So for example, the car or bike body, it is typically waxed, the metal is waxed, in order to ensure that water doesn't stick to it, it doesn't rust. But the same thing creates a problem. The surface, being hydrophobic or disliking water, likes to get attracted towards dust. So whenever there is a bird dropping or some dust deposited on it, removing it becomes extremely difficult. So if imagine there would have been a possibility where there was a switch, just like a light switch goes on and off, you change the nature of the substrate. So and you can just magnify it, you can put it onto a rocket or an aircraft and change the wettability of the surface so that it would glide smooth past the air, or it can rise, it can have enough drag and do that. So with that motivation and several other things like mixing, fouling off, preventing fouling, and finally with the motivation that at micro scale we would obtain something which is a pumpless transport. Because all of us have seen what is a capillary. If we dip a small bore of tube into a pool of liquid, up to certain height liquid rises. And if we keep on reducing the diameter of this bore, the rise of liquid would be higher. So imagine a lag on a chip circuit where the entire thing is governed by capillarity. Okay, so you would not need any external power. So currently Arduino, DIY experiment, you need an Arduino which needs to be powered by a USB port. But imagine a fluid circuit where by simple use of capillarity you can power the entire circuit. You can have the required amount of motion, have the data transfer by simply using the energy that is supplied by translocation of fluid. Mind it is not a perpetual energy machine that I am talking about, not a science fiction. It requires a lot of energy to build a surface, and we basically plan to use that energy in order to gain certain advantage in terms of the surface. So with that motivation, we will try to see how do we analyze a case where the interface or the entire domain is so small that these equations cannot be valid anymore. Okay. So for that we would begin with a particular case study, of a well-known problem, that is flow through a parallel plate or a pipe, and it's a pressure driven flow. So this is ubiquitous. Anywhere you open a tap, you would have this kind of flow. Every morning you brush your teeth, the shape of the toothpaste that comes out on your toothbrush is this. It bulges in the center, and the curvature is towards the end of the ear. And it typically stems from the fact that near the wall there is the fluid doesn't slip, and at the center it has the maximum velocity. Then again, using the same conservation of momentum equation which you studied just now, we can solve this equation and write it in terms of the pressure gradient. And it would come, the shape would be a quadratic equation, and the shape would be parabolic. In 3 dimensions it would be a parabola. And so this is something like any pipe, even a kid would draw, it would draw a shape like this, a parabolic shape. Now this the validity of this entire equation is based on the fact that the gravity and that value is dependent on a quantity which is called viscosity of the fluid. And in a typical case, we say it's a Newtonian equation, Newton's law of viscosity, Newtonian dependence. But that is not valid if, say, let us say we have 10 water molecules lined in a transverse direction. Then obviously you cannot have that 10 water molecules satisfying this equation. So we would need something else other than this. And that balance for a microscale flow is usually characterized by introducing an artificial parameter. That artificial parameter is called slip. So we say that no one has guaranteed if I reduce the system to a microscale, my velocity at the wall would be 0. So if you put y equal to b, you would get the velocity 0. But no one has guaranteed complete exchange of energy and momentum at the wall. So what I do, I would assume that there is something, the fluid molecules next to the wall are slipping with respect to the fluid, and I augment the equation from the solution of this CFD equation with a slip. So with a modified boundary condition I solve. So that gives me the solution for a microscale fluid flow. Okay, and this solution was proposed even before fancy computers and CFD techniques came in, and it was proposed by Navier. Navier from the Navier-Stokes equation. He proposed it in 1823, where he said that fluid molecules would be striking, there would be momentum exchange, and if the exchange is not complete, there would be something called a slip length. So basically the same trajectory can be extended, and beyond the wall I would get sort of a, the fluid molecule the center of the fluid molecule would feel that it is not confined, but the actual wall is somewhere a little beyond the, or rather the perceptible wall is a little beyond the actual wall. Okay, so sort of an artificial condition by which I would try to match the observation with the equation. That does pretty well for most of the cases, especially when we are talking about tens of microns. Okay, but then we hit a problem. What is the problem? All of us have seen this experiment, right? Water on a glass surface would completely wet it. Okay, it would spread like a film. Mercury on a glass surface rather forms more like a sphere, a solid ball, and you a drop of water on a lotus leaf, and all the poems and songs about it. But there is a problem here. Now, if a liquid film is spreading on the surface, basically what is spreading? If I expand this droplet view, zoom it very much, probably the smart mode would be able to do it, but I did it on PPT. You would get a rectangular wedge, and what would happen? One end of the wedge is going to slide. So what is that basically? That is basically motion of the fluid molecule next to the wall, which is not supposed to happen. And if we go back to our good old equation, you will have no classical CFD equation accommodating for what is the surface. Here you do not say, okay, it is an aluminium, silver or a plastic surface, and hence value of P should be this. That we do not do. So sort of, in order to do that, we can artificially include the effect of this surface into the slip length, or there is another way to do it. Instead of using classical CFD, we try to use the Newton's second law. And all this, so these are basically, you see this red white structures, probably at your distance this would be red dots. This zoom that. And it zoomed after. Let me see, can I go back? No, it requires technical help now.
Let's stop.
Stop. Thank you. So these red dots are basically water molecules, and if I try to track these water molecules, instead of trying to have a quadratic equation to solve it, I solve it using force equal to mass into acceleration. And from that, I try to solve anything that is in the range of 1 nanometer to 1 micrometer. That would give me an exact solution. And that is where combination of the surface characteristic, that is the wettability, to the fluid characteristic, and hence the liquid solid interaction that we talk about on lab-on-a-chip circuit comes into play. And sort of, in order to integrate this, we can take two approaches. One approach can be statistical. Statistical approach are typically random walk approach, where we say that the fluid molecule, we have certain fluid molecules, they are sort of placed in a grid and they can move in any direction. Okay, so it is possible, like if I take a two-dimensional, it can either move forward, backward, and I give them randomly some orientation and try to see how they evolve. Similarly, for two-dimensional, they would have 4 places, three-dimensional, they would have 8 places, and so on and so forth. So that is sort of a statistical simulation called Monte Carlo simulations. But in order to get greater perspective on what is the force acting on the system, we can do some deterministic simulations, which is molecular dynamics simulation. We'll briefly go through how we do the molecular dynamics simulation. So yeah, the basic equation is again Newton's second law, force equal to mass into acceleration, and we start with the geometry. Okay, so whatever we are trying to solve, lava blood flowing on in a small conduit, or a droplet spreading somewhere on a lotus leaf. We take the geometry and put everything in a particular lattice. That can be any sort of lattice given the chemistry of the unit. So we have the solid, we have the liquid, and from that there would be sort of some particles in the space. They would have some interaction because they might have some charge. They would obviously have some mass, which doesn't matter. Gravity at this scale doesn't play a role. So, and based on that, they would have some field, because we know that two molecules which are similar, they would have a sort of a cohesion force. Two dissimilar molecules would have an adhesion force, and with this they would attract each other, repel each other, and that force field is sort of known classically. Okay, so we try to find that force field, and if we digress for 2 minutes and talk about the history, the determination of this force field also came somewhere around the Second World War. Since we are just discussing Second World War, so it was for an unrelated year, the Manhattan Project. So in Los Alamos, people were trying to design the atom bomb, and it was very important to predict whether whatever nuclear fission reaction is going to happen, whether it would actually create a bomb or it would be so destructive that everything would be destroyed. So they needed actual deterministic motion of the particles, what is going to happen after the bomb is dropped. And these simulations played a very important role in deciding how to design the bomb and what it is going to happen. Okay, so that sort of gave birth to Monte Carlo simulations and molecular dynamics simulations, and after the Second World War, the Los Alamos primer was declassified and it became a topic of research. And but that basically gave us the background that when there is a cluster of particles, I can find out what is the force that would be acting between them, because remember, force is commutative. If, for example, I am a particle here, if you have to calculate your force on me, you can either calculate it from your end, which is difficult, but you can do it from the other way, which is my force on all of you. So, and that is quite simple, although when we talk about millions of particles, it is not simple. You need a good coding and high performance computing systems, but nonetheless you would obtain the total force. Now total force is equal to mass into acceleration. From acceleration you can integrate it over a finite time period to get velocity. Velocity again you integrate to obtain displacement. Now whatever you use was your initial lattice, you displace it by that displacement, you get 0.2. You get a new force field at that point. Repeat, acceleration, velocity, displacement, 0.3, so on and so forth. You get a deterministic evolution of particle. So if you use this simulation and apply it onto different surfaces, so you need not do anything else, just choose the correct combination of surface and air. You can get transition from water to mercury type of behavior on a surface, and that is the fundamental and interesting part of molecular dynamics simulation. So now using these simulations we can do a lot of things. So this is sort of the background of how force fields are generated. So it is the typical understanding of force field. We will try to explain it from here. Is that when two particles are very far away from each other, they tend to do not interact. Okay, but as they come closer, they would start interacting because the electrons of one particle would see the nucleus of other particle and vice versa. So there is a sort of an attractive force. When there is an attractive force, the tail goes down. Okay, so you see that below part of the curve as you move from right to left. So negative potential would indicate attraction, and they get attracted up to a point where R equal to D. So at that point, the particles realize, okay, no, there is a nucleus on the other end, and there is a nucleus here which is both positively charged, and the electron cloud is negatively charged. So no, increase the repulsion, and then the energy decreases. But by that time, by inertia, they are already coming closer. Okay, so it is just like two human beings. Far away you like people, and as you come very close, you start hating them. And at a point, you would be so close to them that the nucleus would overlap and the repulsion would increase. So you see, it's a slightly curved line. It's not absolutely vertical, but curved line, and that would basically sum up the potential of any interaction. And this potential was proposed by John Lennard Jones. The attractive part of the potential is given by sigma to the power 6 divided by r to the power 6, r being the distance between two particles. Sigma and epsilon are the values of the point of zero potential, the distance between 0 and 0 potential here, and epsilon is the depth of the potential well, the lowest point of the potential well. So it is, by solving your Schrödinger's equation, you do a fitting and you get, and by some comparison of the electrostatic, the strong and weak forces of particles, you put the value sigma to the power 6. Now, the entire thing was done in an era where you needed to bomb Japan immediately. So, and computers were not very easily available. So, they did not did a lot of effort in calculating the repulsive part. They simply squared the attractive part because they realized repulsion is a short range force. From far away, everything is attractive. As you come closer, you see the electronic cloud overlapping. So, repulsion would be shorter in range. So, the power of R should be greater than 6. And if we do something like 8, 10, calculating that becomes really cumbersome. We do not have that much of time. So, we just square r to the power 6 and r to the power 12. So, that totally sums the repulsive and attractive part. But it turns out that works very well. Until date, we highly use this formula to solve our nanoscale and microscale problems. And now that sums up the entire thing. You start with an initial configuration, take the potential, calculate force, repeat. Force gives you acceleration, acceleration gives you velocity, velocity gives you position, get the trajectory. Now once you have the trajectory, you can do a lot of things with it. Like what? It gives you what is the rate of transport, how fast mass can be transported, how fast momentum can be transported, and if at all there is a possibility of energy harvesting or energy transport using it. So all that information is held in the trajectory, and then you can calculate properties like viscosity, diffusion coefficient, and other things. But here we will study one specific application, that is towards thermal management of solids. Now, so this is a typical system that would look like this. You see, this is actually molecules. You are calculating the velocity, and you see the zero line is there, and you typically get a slip. So whatever Navier proposed in 1823 as a mathematical tool, we can actually get it an in silico experiment from molecular dynamics. Actually trace the molecular path and get that. So now coming to our application. So our application is related to heat sink. Since this course also is relevant for thermal engineers, so and we have people from instrumentation and electrical here as well. So one of the challenge today is to design a heat sink for a converter inverter, because if you have ever seen an instrumentation lab, a converter is of this size which is placed on a heat sink of this size, right? And that is very challenging because in space exploration or say battery technology, now we are shifting towards renewable energy and batteries are very important. If you do not manage them thermally properly, that's a huge problem, because traditionally if you take a very sturdy electrical component like a transformer, Okay. So how does a transformer fail? 90% of the time it is thermal failure. Electrical failures are very rare. Okay. Obviously, the big sound is the relay sound. Typically, failing of transformer is a spectacular event, but if it fails, it is because of a thermal failure. So, designing of thermal heat sink and making it compact. You are designing an electric vehicle. All of us have seen heat engine in a bike or a car, regular car. But you are designing an electric vehicle. Unless until the heat sink becomes very compact, very light, that is not advantageous. Okay. So what are the challenges in designing a small heat sink? No, there are certain inherent properties which make design of a smaller heat sink always advantageous. What are these? You get a lot of surface area. So with the same amount of fluid, if you are doing fluid cooling, if you instead of moving them through 1 mm pipe, if you are moving them through 1 nanometer pipe, quite impossible. But if you are doing that, you get significantly increased surface area for the same volume of fluid. So it should be advantageous. But what is the problem? The problem lies in the fact the pumping power. How do we pump the fluid? Capillarity is good. We just studied capillarity. Capillarity is good, but it is for just one drive of the fluid. Once your channel is wet, you cannot again, you need to have a mechanism to drive it out before you can use capillarity. So, towards it we would try to incorporate aspects of a lab-on-a-chip technology where solid fluid interactions are used to improve the thermal performance of the cycle. And that gives us a background of, I believe this is something, high school stuff or, UG stuff where, thermal boundary layer develops for a heated plate and the temperature would decrease as you move away from the wall towards free stream. And the heat transfer, if you are trying to cool that brown colored plate using a liquid or a air stream, the maximum heat transfer occurs in that zone where your temperature is changing, because obviously in order to cool down you need a temperature difference. So sort of if we can play around in this zone, it is quite advantageous. And indeed we can, because we just saw the example of pressure driven flow where the entire slip length is impacting the zone next to the wall. So whatever augmentation of flow or slip or modified boundary condition, whatever name you want to give to it, it occurs next to the wall. So, we just put two problems together, one thermal transport occurring next to the wall, the second a modified transport occurring next to the wall, combine them and we can obtain augmented heat transfer next to the wall by reducing the pumping power. And do we try to address the problem of internal force convection, which in layman's term we call the designing of a heat sink. Heat sink which would cool a circuit like this. Okay. So these are some mundane equations, and there's something that has happened to this slide on the smart TV. So let us skip it. So under the condition of a constant heat flux, your temperature is changing, and we need to take away this temperature in the fluid stream. Okay. So this is a much cleaner slide which would help us. So we start with the IC chip, which needs to be cooled by a very small heat sink. And the design of heat sink is challenging because typically your CPU or engine heat sinks are huge. But with lab-on-a-chip technology, we need to shrink the heat sink. And our proposition is that we sort of would try to modify the solid fluid interaction on the walls of the heat sink so that we get augmented heat transfer in the heat sink. So we would design a small scale heat sink so that the fluid flow at very low pressure drop is capable of removing the heat. So we try to develop a three-pronged approach in order to address this. So what are the three-pronged approach? So firstly, we take a double layer. So this is very traditional. If you see any heat sink, it's a fin and tube heat exchanger. Heat exchanger, if you typically have seen in industry or in your course, it always comes in pair. So if you get a counter flow, you would always have a better heat exchange. Okay, that is something like common intuition when you need to give a cold press or a hot press. Okay, so that is a counter. So we design a counter flow heat exchanger so that cooling is more efficient. The second technique is that we obtain a sort of tapering of the channel. Now, tapering is, instead of having the upper and the lower heat exchangers of the same cross sectional area, we change the boundary, we give an angle or taper to the boundary. How would this help us? We know when fluid moves through a converging cross section, the velocity has to increase, because velocity into cross sectional area is constant. Greater velocity would mean greater transport, right? So there would be steeper gradients near the wall because of that convergence, and steeper gradient would mean thinner boundary layers. Thinner boundary layer means more gradient in temperature and better transport. So sort of this is another passive technique by which we try to enhance the heat transfer, and finally we modify the surface. So basically, typical chemical vapor deposition or other techniques can make the surface hydrophobic or hydrophilic. It is similar to having a wax polish on the surface, on a metal surface, or the polish like this which doesn't allow water to stay. That would drastically reduce the amount of pumping power that would go into pumping of the fluid. So using these three techniques, what we propose is a heat sink which would not only reduce the pumping power but would also enhance the heat transfer that is occurring in the surface. So obviously when we talk about introducing a modification, we have to compare, because if you try to cool electronic chip with a bucket of water, it would obviously cool down, but that is not our agenda. We need to optimize the pumping power with the cooling rate, and for that we propose our model which looks like this. So there's a three-dimensional layer of the left-hand top corner, and this is the cross-sectional view where fluid would flow in opposite direction, cooling the whatever your microchip or battery, whatever is there, and these are governing equations. Again, partial differential equation. Thermal performance here, and in order to compare performance of two heat sinks, we define something which is called a performance factor. So it is basically a sort of a ratio. Just like you invest money and you do a ratio, like what is your return on investment. So similarly here we develop something like a performance factor, which is the thermal cooling that is obtained as compared to the pumping power that we give, and we can obtain it for various values of tapering factor and various Reynolds numbers. Okay, and from there we can obtain the maximum, the optimum value of Nusselt number. Obviously, Nusselt number would keep on increasing as you give more and more pumping power to it, but we will get an optimum performance factor at some sort of. So very interestingly, we do not obtain it for a hydrophobic surface, because hydrophobic surface would totally repel water and the pumping power would increase. We do not obtain it for a totally wettable surface, but we obtain it some sort of an angle of 40 degrees. So we understand that contact angle is sort of 90 degrees in between. Anything acute is hydrophilic, wetting, anything obtuse is hydrophobic for water. So we see that the maximum performance is obtained at a optimum value of contact angle for partially wetting. So if you remember those droplet, so the top case, the case on the top where it was forming a acute sort of a part of a sphere or semicircle, and which is sort of counterintuitive to begin with, because we always believe that the least pumping power is obtained when your surface is hydrophobic. Like if I polish a surface, removal of water becomes easier, but as removal of water becomes easier, we also have to appreciate the fact that the layer, the interface, the solid fluid interface is replaced by a depleted fluid zone. So what is wettability? Wettability is nothing but how your fluid is interacting to the surface. The moment my fluid doesn't like the surface, macroscopically what it will do, it cannot, walk, like you do not like the glass, you can get up. A fluid molecule cannot do that, right? It has to, by gravity, it has to stay there. What it would do, if water is 1 gram per cc, you would get a slightly depleted 0.95 or 0.9 gram per cc next to the surface. But that reduction in number of molecules is sufficient to impede the heat transfer. So basically what is happening with hydrophobic surfaces, as you can see from the Nusselt number. So typically, you know what a thermal engineer would do, calculate the Nusselt number. You have done in your undergraduate book, you calculate Nusselt number and you see higher Nusselt number, better heat transfer. That is not the case. Higher Nusselt number, faster flow, but that faster flow doesn't always mean that the solid is transferring heat to the fluid. It just means that the fluid is flowing fast and you are getting fresher cold fluid in the heat sink at the expense of power. In order to have most out of your power, you would have to go for an intermediate wettability where the fluid and liquid are interacting, heat transfer is occurring properly. At the same time, you are having to supply some pumping power in order to achieve your cooling. So, you know, this is a sort of an analysis which you can typically do for a lab on a chip circuit. So, this is a very basic example, although this is a research level example, but a very basic example. You can, you know, proceed in several, since you know this is a faculty development program. Out of this you can try to combine the boundary condition from molecular dynamics and the continuum equations from CFD and do a lot of stuff regarding energy transport, thermal transport, momentum transport of anything where there is a fluid solid interaction, be it, you know, aircraft propulsion, transport of hydrogen, which is, you know, next big thing, or, you know, ship moving in the ocean, all those things, or, you know, some small virus flying in the air trying to bring in another version of COVID. So all these interactions can be sort of a interfacial solid fluid interaction, and we can use it solving this. And, you know, there are further, you know, once you get a grip of that numerical solution, you can do for several optimization scheme and get the optimum value of tapering factor, channel size, contact angle to get the maximum performance. So on and so forth, you can do a lot of things. So in conclusion, you can design any circuit, any lab on a chip circuit, whatever is your goal, fluid transport, heat transport or whatever, and you will optimize it from the macroscopic boundary conditions of CFD, microscopic boundary condition of molecular dynamics, combine them together to get the optimum fluid solid interaction. Yeah, I would like to thank you all. Yes, questions.
Last slides, I have seen the slip length is vertically downward. Is it possible?
Vertically downwards, yeah, vertically down. It is basically, see, if your channel is, let me do this. So it is basically flow is occurring in this direction. Horizontal, flow is horizontal. The wall is this way. So the fluid, since it is slipping on the wall, if I imagine that there is a no slip boundary condition valid, after some certain distance, there would be a sort of imaginary wall where the fluid velocity is zero. So it is just the orientation in which you draw it. The molecular dynamics result I have drawn in reverse orientation, 90-degree rotation. So it is vertical or horizontal. It depends on how you draw it. Also, it is the most simplistic here because you see it's a linear here. So it's a linear extension. You can have, typically you would have a parabola, you can extend the tangent, or you can extend the parabola and you would get the first order slip, second order slip, and so on.
I have 3 questions. First of all, you have seen that there is a pumping process. Right? You have told that there is a no pump necessary because there is a capillary action.
Yes.
So what is exactly meant by pumping power?
Pumping power is basically the power that is lost in the viscous interaction as the fluid moves on the surface of the conduit or the pipe. So that is the pumping power. When I say capillarity, doesn't need pumping power, that is only for once. A dry capillary bore would allow the water to rise, but once the capillary bore is filled, you cannot get the rise. Hence, you would need some pumping power to overcome the viscosity.
That's what to work on the viscosity. And one second question is that molecular dynamics simulation, what is that? That is in the macroscopic or microscopic?
That is in the microscopic.
Microscopic level.
Yeah.
And third question is that what type of actually this is a interaction between the fluidics and the electronics, right?
Yes.
The electronics, when you are designing the chip or etc., whatever may be, so what kind of chip is used generally? What is the analog or the digital circuit?
That's a very interesting question. Thank you for asking it. So, that is another whole plethora of EA where we talk about the chip or the thing that we are trying to cool. Because here we assume a constant heat flux, which is hardly the case in real life. So, if you go into actual analog or digital chip design, your hotspots would vary depending on your applications. So, cooling the chip uniformly is not the solution for those cases, and there you would require targeted cooling. So for that, there are a whole lot of other lab on a chip applications where you use droplets instead of a continuous flow of fluid in order to target them. This here we sort of think of the your electronic chip as a black box and say it is just a 1 centimeter by 1 centimeter area which is radiating 200 watt per centimeter square to keep a factor of safety. But yes, we also work on analog and digital circuits where we target the hotspot and use the temperature of the hotspot itself in order to induce Marangoni flows, temperature generators, so that there can be a targeted cooling of hotspot. Especially with respect to battery circuit, because batteries are used, but the hotspots are within the battery.
Battery means analog.
Batteries are lithium-ion battery. That is totally analog.
Analog.
Yeah.
So we move to digital circuit. Generally, analog is used.
Sort of electronic circuit, even if it is digital, the heat sink would be common. Right. Just the way you cool it would differ.
There is that channel, micro channel. The middle one is tapered.
Yes.
Other two is parallel. Why?
So basically, a heat sink, if you so heat sink has to be, even this is the heat sink. If I need to cool my chip, it has to sit on the heat sink. Now fluid has to flow from this direction and this direction. I can only have the middle wall as taper because I need, airflow or whatever here. I need this to make contact with my circuit chip, so they have to be flat. The only portion where I can include tapering is in the middle, so that I can get differential flows.